We're happy to have Peter Ozsváth from Princeton to talk today. And he will speak about the border approach to link Floer homology. And this is not the Western Hemisphere.
Sorry, I'm, yeah.
But we will listen to your talk nonetheless. So,
well, we should vote on it.
All right, great.
Well, thank you very much. Thank you all for being here. It's so nice to see so many friends on the little windows. A little nice and a little frustrating. It'd be nice to just talk to you guys in person. But anyways, thank you for coming. Thank you for the organizers for inviting me. And I'm especially grateful to Octav for kind of saving the world. If there's ever any such a thing as a broader impact statement, I think introducing a little bit of sanity should be on the top of it. So thanks for doing this. This is wonderful. Okay, so I'm going to talk about a bordered approach to link Floer homology, and I'm going to still try to figure out. Okay, so this talk will concern link Floer homology, which is an invariant for links in the three-sphere, introduced, I think a paper was put on the archive in 2000. That's not possible. Anyway, it was introduced at some point and defined with Zoltan Sabol, which is it's an elaboration on not Floer homology, which was defined by us and independently by Jake Rasmussen in 2003, building on Haggard Floer homology. So what I'd like to do is I'd like to give an algebraic or bordered approach to computing this invariant, which is building on the bordered Floer homology developed by Robert Lipschitz, Dylan Thurston, and me in a slightly in the context of Haggard Floer homology. And my talk will be a step beyond. I mean, I've been lecturing about computing not Floer homology for a while using this bordered approach, and so this is the generalization to links. Okay, so a knot or link can be presented as a closed curve in the multi-curve in the plane with crossing data. So here's a picture of a link, a link. There's a measure of the complexity of a link, which if your link is given with an orientation, then you can. There's a theorem of Seifert that says that the link can be realized as the boundary of an embedded surface with boundary in the three-sphere. You can try to find the minimal genus of any such embedded surface. And that's going to depend greatly on the orientation of the link. So on the left, I've got a twice punctured genus 1 surface, and on the right, I've got an annulus. So these are for the two different orientations on this torus link. Okay, so that's the Seifert genus. And so you can think of this, if their link were or not, this is sort of fundamental measure of its complexity. So there are various elaborations of the Seifert genus. If your link has L components, then the relative two-dimensional homology of S3 or R3 module relative to L is an L-dimensional vector space. And for each relative homology class, you can find a surface that represents it. And one can ask, what are the various, so you have a function from the two-dimensional homology to the integers that tells you the minimal genus of a representative. And there's a very pretty formulation of this due to Bill Thurston, which is you start by defining the complexity of a, sorry. Sorry, this is sort of sad notation. This should be a chi sub minus. So chi minus of F is you take a possibly disconnected surface, you throw out all the spheres, you take the Euler characteristic and multiply by -1. That's a measure of the complexity of a surface. And Thurston recognized that you have a semi-norm on two-dimensional relative homology that you get by just finding the minimal complexity of a surface that represents a given relative two-dimensional homology class. And so, in fact, this function is linear on rays, so it extends by continuity to a real valued function on the real two-dimensional homology, and if you can look at its unit ball, that unit ball is a polytope, and that polytope governs the minimal complexity of surfaces representing two-dimensional homology. So this gives a sort of pretty picture for how to understand these minimal genus representatives. And in fact, it's convenient to think about the dual polytope, which is, so the relative two-dimensional homology is Poincare dual to the one-dimensional homology of the link complement, and so a semi-norm on a vector space determines a possibly degenerate norm on its dual space, and that's the dual Thurston polytope. So here's an example. Here's a link. This is some pretzel link, or which you might call the Kinoshita-Terasaka link. It's and here's its dual Thurston polytope, which is this little skew parallelogram in two-dimensional space, and that tells you the minimal genera of various surfaces that bound various homology classes in here. So okay, so that's something that one might try to understand topologically about a link, and I'm going to now describe how we compute link Floer homology, and one of its maybe best applications is to understanding this polytope. So let me say a little about link Floer homology, but before I do that, I'm going to say some more sort of fundamental things. And a lot of this is based on this idea of Kaufman states. So this were introduced by Lou Kaufman to compute the Alexander polynomial of a knot. And what we're going to do is we're going to represent a link, an oriented link, by its projection, and we're going to put on some additional data. So we put a star on one of the edges. So one of the edges is going to be distinguished. In the course of my lecture, I will also choose a edge on each different component of the link, though that's not yet important. And I will typically take that to be the local minimum of the height function. So I'm going to think of my projection on the plane, and I'm going to think of the height function, and I'm going to just distinguish the global minima of each of the components of the link with a big gray dot. Sorry, not each, but all of the non-distinguished ones. So just said again, I'm going to have a link projection. The global minimum I'm going to put a star on, and I'm going to forget about that component, and all the other components I'm going to put a big gray dot on somewhere on the edge. Okay, so that's the basic data how we represent a link. Now a Kaufman state is a map that associates to each crossing one of the four adjacent quadrants. And it's subject to the following constraints. No two dots lie in the same region, and no dot is adjacent to the distinguished edge. So here's an example. So of these four quadrants, do you see my mouse? Is that, okay. So of the four quadrants, I put dot anywhere here or here. I can't put it here or here because the star is here. So I have to put it either here or here. Again, over here, I can't put it here or here because then there would be two dots in the same region. So I can put it here or here, and so on. So there are these just rules, and that's what a Kaufman state is. So the next step is that one can compute a link has a multivariable Alexander polynomial, which is, if I've got an L component link, then there's a polynomial in n variables. for an n component link. And you can determine it as it can be thought of as a sum of Kaufman states. So I'm going to put a monomial in various of the variables at each of the quadrants. So to be more precise, each component of the link is, the components of the links are in one-to-one correspondence with the variables in my polynomial ring. And at a given crossing, if it looks, I oriented my link, if it looks like this, and suppose that this component is labeled by the variable t, and this component is labeled by the various s. So I'm going to put these various monomials in s and t around the 4 quadrants. And now what we just do is we sum over all the Kaufman states of all of those monomials. And in that way, we get this polynomial in T1 through Tn. And that's the Alexander polynomial. So that's a perfectly reasonable definition of the multivariable Alexander polynomial. There are more conceptual definitions. And in fact, one thing that you see almost immediately is that the orientation, I didn't use orientation in a significant way. I used the orientation to identify the group ring on the first homology of the link complement with the polynomial algebra in N generators. And now I realized something. So first of all, I took one of the most unfortuitous sabbatical breaks this last year. So I missed out on all the fun of online teaching. So I'm a relative newbie. And I'm also dependent on audience feedback to keep me from going at in really fast speed. So can you guys somehow indicate if this is a reasonable speed? I can see Lisa and Octave right now and a caricature of Helmut. So maybe Lisa and Octave will be my target audience. Is this a reasonable speed?
It's a reasonable speed.
Okay, good. Hello, Denis. If something is a reasonable speed for Denis, that doesn't really have any information whatsoever, but okay, good. All right, so moving on. Okay, so the link, so link Floer homology is a multi-graded abelian group or vector space over Z mod 2 if we're being lazy. And if you have an L component link, then the grading set is kind of L plus 1 dimensional. There's one dimension that measures it's a Maslov index. It measures a kind of dimension, and all the others you can think of as sort of winding numbers around the various components of the link. And so there are many versions of link Floer homology. I'm going to talk in this talk about the simplest version, which we called HFL hat. And so this is this graded vector space with an L plus 1 dimensional grading set. All right. So invariantly we can think of the L dimensions of grading as graded by the relative homology of gosh. Though I should have said the one-dimensional homology of the link complement. All right, so now there's an Euler characteristic where you keep the L of the dimensions and you look at -1 to the D, where D is the remaining degree. And the statement is that that Euler characteristic is the Alexander polynomial of the link. So this is related to the Alexander polynomial. And it is also related to the Thurston polytope in the following sense, that you can look at, if you think of the grading set of the groups as by the first homology of the link complement, then you can take, so what I didn't say is it's a finite dimensional vector space. So there are finitely many first homology classes on which the vector space is non-trivial. So we just take the convex hull of all of those points in first homology, then we get a polytope in the first dimensional homology. And the statement is that that polytope determines the dual of the Thurston polytope. And the way it does is you take that polytope and you add to it a hypercube of side length 2, and then you get a bigger polytope, and that's equal to the Thurston polytope. And if you want to think in terms of formulas, the statement is simply that the Thurston norm of the Poincare dual of a first homology class, plus a correction term, which is measuring the evaluation of that first homology class against the meridians of all the link components. So that's somehow, that's some correction term. That's equal to twice the maximum first homology class. This should be H1 of L, I mean H1 of S3 minus L. So the maximum of the evaluation of that first homology class on the relative two-dimensional homology class, some intersection pairing. And you maximize that overall points in first homology for which this link Floer homology is non-trivial. Okay, so that's a statement. This is an analog of a theorem of Kronheimer and Rovka in the context of gauge theory. They proved the analog of this for closed 3 manifolds rather than links. And I wanted to say that very elegant proof was given this shortly after we proved it by András Juhász using his sutured Floer homology. Okay, so here's an example. This is the link that we talked about earlier. Yeah, I guess the one advantage is that I can write on the blackboard really, really fast. Okay, so here's this example. And what I've drawn here is, this is the relative two-dimensional homology of this, the first homology of this link component is two-dimensional, so I got the plane, which is the first homology. And over each lattice point in the two-dimensional homology, I've drawn the dimension of the corresponding Floer homology. So for the lattice points I didn't indicate, the Floer homology is all 0-dimensional. And here are the places where it's 2-dimensional, here's 4-dimensional, the origin is 6-dimensional. And what I didn't draw was the other grading, which is the Maslov grading, which is 3rd dimension. And there's a sort of evil plot to make that, those other characteristics are all 0. So this, the 2-variable Alexander polynomial of this link is identically 0. And yet the Floer homology is non-trivial, and this is the dual Thurston polytope that I drew earlier. And you can just sort of see that if you smear this out by a 2x2 square, you get something that geometrically looks like this. So that's the relationship. Okay, any questions? Or jokes, or, okay. So I'd like to describe a computational approach to computing link Floer homology. So it's a variant of Lagrangian Floer homology. So in 2006, building on earlier work of Shuchait-Sharkar, Ciprian Manolescu and I gave I gave a combinatorial description of link Floer homology in terms of grid diagrams, which is really wonderful, and you can teach it to undergraduates, and we have a book about it, and I recommend it very strongly. On the other hand, for the purposes of this talk, I'm supposed to say how bad it is. So the real point is that for a link with n crossings, the link Floer homology is presented as the homology group of a vector space whose dimension is roughly n factorial. I think it's n plus 2 factorial in the worst case, but that's kind of horrendous. So even when you look at the smallest possible links, the homology group that you have to compute is an insanely big dimensional space. It's a very nice because the differentials in that picture are just rectangles. They're very simple objects. But I'm going to describe here a different approach to computing, where you get much fewer generators. You probably get, I mean, it's closer to the optimal, actually. For an alternating link, you get, you get as many generators as you have groups. So it's optimal for alternating links, which are kind of very bad from this point of view. But at any rate, it's hard to come up with something that's going to have fewer generators. The problem though is that the differentials are much more difficult to describe. Okay, so that's okay. So the basic point is going to be this idea of slicing link diagrams, and the idea is the following. So I'm going to draw my link diagram on the plane. It's a I forgot to put a big gray dot on the second minimum, but I'm going to take my link diagram and I'm going to just cut it horizontally into pieces, and I'm going to arrange the stars at the minimum. So above each horizontal slice, I have what we call upper diagrams, and below we have lower diagrams, and in the middle we have middle diagrams. Okay, and to an upper diagram, what we're going to do is we're going to associate a kind of algebraic structure, which is called the type D module. To each slice, we're going to associate an algebra, and to each lower diagram, we're going to associate type A module. So I'm going to describe those objects in a little more detail in a moment. But let's see what I wrote. This is a work inspired by work of Lipschitz, Thurston, and me for 3 manifolds. And the statement is that link Floer homology can be computed by a certain successive tensor product of bimodules over that algebra. And this statement is a theorem about counting pseudo-holomorphic curves. It's analogous to the pairing theorem in the closed context, and it generalizes some earlier papers of ours on the archive. Okay, so so now I'm going to sketch the ingredients that go into these successive tensor products. Okay. Any feedback? Any?
So
yes.
So I think many of the people here, me included, are not so sure about the the version. I think this combinatorial version that you mentioned that has many generators of the order of n factorial and but a simple differential.
Yeah.
So will you recall that a tiny bit later, or how?
No, I won't talk about it at all. My talk is entirely about something different. But this is a wonderful book.
Right, okay.
And one of my co-authors is in the audience. I recommend it very strongly. I actually give it to my undergraduates. Try to get them to go away. It's and it doesn't work so well for that. So I recommend it.
All right, but Peter, the reason why you have n factorial, can you say why you have n factorial generators only?
No, n factorial is not only, it's why do I have so many is the question. And the reason is that the diagrams that you use to describe the knots are quite complicated. So here's, I guess I am going to talk about it. So here's a knot projection of the trefoil. That's a nice simple object. To look at the associated grid diagram, you have a 5x5 grid.
Oh, okay.
And it turns out that the generators of our complex, what we're really doing, who am I talking to? We're doing a computation in the 5th symmetric product of the tori. And it's got 2 Lagrangians in it, which are the tori of horizontals. You take the product of the horizontal circles, that's a torus, and the other Lagrangian torus is the vertical circles. And those two, the number of intersection points of those Lagrangians is n factorial, if n is that size of that grid. So that's the answer.
And the reason why the differential is so simple is that in principle you can see the holomorphic curves very easily, and they're just
very simple. The only holomorphic curves with Maslov index 1 are rectangles. So it's a completely combinatorial description.
But for us, a rectangle doesn't compute a differential generally. It computes like a mu3 operation or something.
I'm sorry. So these are honest disks in the second symmetric product of a Riemann surface. So they're rectangles with an involution. So when you divide out by that, you get a bigone.
Okay.
My point just about calling them rectangles is that sort of there's no, the conformal story is completely straightforward. There's always a bigone if you see a rectangle in the picture.
All right. Okay. Thanks.
My pleasure. Any other questions? Okay. Okay. So now I'm going to talk about something else, which is this bordered approach. And like I said, we have various ingredients, and the simplest ingredient to describe right now is what we associate to a horizontal cut. And what we associate to a horizontal cut is as a curved algebra, which is which is simply an associative algebra with a preferred central element. But I'll draw it like this. We're going to draw two trees. One of them is a tree with two inputs and one output. That, of course, that's the tree that represents the multiplication. And there's this tree that has no inputs and one output. That's the central element. And there are two relations. One is that this central element is central, which is to say that when I multiply on the left or on the right, it's the same. And by the way, I'm always over Z mod 2, so I didn't bother with any signs. And the second relation is that the algebra itself is associative. So this is the data that we're going to associate to a horizontal cut. And now, what's the data that we're going to associate to an upper diagram? Well, it's going to be a curved type D structure over that algebra. So what's a curved type D structure? It's a map. I've got a finite dimensional vector space X, and it's a type D structure is a map from X to A tensor X. And the way to think about it is that suppose that you have a free A module, and you have a chain complex of free A modules. Then you take a generating set for that, a basis for that that chain complex, and you look at the differentials of elements. So the differentials of each element is going to be expressible as A times other generators. And the structure relation is that if I take this matrix Aij, if I multiply it by itself, I'm supposed to get curvature times the identity map, and that's just that's what I'm saying right there. And this is the same thing as a matrix factorization of Khovanov, that Khovanov and Rozansky considered, and the abstractions from Fukaya, Ono, Ota, and O. So these are familiar objects. I want to write the type D structures graphically, and because I prefer pictures to formulas. So the operation, I've got this kind of red vertical line. So what this means is that this is sorry, blue vertical line. That the blue vertical line represents X. So in comes an element of X, I hit it with my differential, out comes an element of A, tensor an element of X. And the relation now can be expressed like this, that if I apply the differential twice and I multiply the outputs, then that plus just the identity map with the curvature spat out should be equal to 0. Okay, is that clear enough? So, you know, this is somehow, okay, it's pretty simple. Now, the next object are A infinity modules. So that when I say a type A module, that's just an A infinity module. That's the final ingredient that we need algebraically. And that object has a bunch of operations. One is a differential, another is an action by the algebra, and then there's an M3, which is action by two algebra elements coming in and acting. and so on. There can be n algebra elements coming in. And the curved relation are that sort of d squared, this is like d. D squared is the same as action by the curvature. That's one of the relations. Then the other is that if I take the action by an algebra element and take d of that, then if I try to alternatively take d and then act, that's the same as these higher actions with curvatures stuck in it, and so on. So you might not, if you don't know what I mean by and so on, it's the following. Both of these trees are, if I contract, both of these trees have a single internal edge in them. And if I contract that internal edge, I just get a tree with a single vertex in it. So these are all the different ways of expanding that one input, one output tree with an edge. And similarly, if I contract, all of these have a single edge in them. If I contract, I just get the tree with two inputs and the tree with one internal edge, with one internal vertex, three inputs and one output, and so on. So there are, in general, I'm going to take the corolla with n inputs. So I've got n inputs, a single vertex and one output, and I look at all the different ways of inserting an edge into that. Those are the relations in general. Okay, so these are the curved modules that we have. And the final algebraic operation that we have is a way of taking a type D structure and a type A structure, or an A infinity module, and taking their tensor product, which is going to now be a chain complex. And the chain complex is described as follows. I've got coming in an element of the type A side and the type D side. Well, one term just differentiates on the A side. Another term just differentiates on the D side. Out comes an algebra element, and then it acts on the type A side, and that gives me an element. And the next term, which is maybe the funny, is that first I apply the differential on the type D side. Out comes an algebra element. Then I apply the differential on the type D side again. Out comes a different algebra element. Then those two algebra elements act simultaneously on the type A side, and so on. So in general, I'm going to just apply the differential on the type D side n times. Out are going to come kind of n algebra elements. They're going to all come and act on the type A side. And it's not hard. It's kind of entertaining to check that this satisfies d squared equals 0. And so just stepping back for a moment, all the way back. Oh, this is the problem with one of these talks. Stepping all the way back here. So when we have a knot diagram, forget about the purple region for a moment. So I just had this blue upper diagram and a red lower diagram. I'm going to describe an algebra, a curved algebra associated with this horizontal cut. To the upper diagram, I define a type D structure. To the lower diagram, I define a type A structure. And the statement is that the tensor product of those two objects computes the link Floer homology of this link. And there are various elaborations of this, but let me just leave it at that for the moment.
Any other question?
Yes.
Do we see any of that curvature stuff in that tensor product?
It's beautiful. In the proof that d squared equals 0, the curvature disappears. So okay. when you yes, you see the curvature. You see the curvature in the type D structure relation. You see the curvature in the type A structure relation, and then in the proof that d squared equals 0, when you see the curvatures coming in, they cancel. So the key point is that your type D structure and your type A structure have to have the same curvature in order to get a chain complex. Hi, Ina, nice to see you. Okay. Okay, so here's our, okay, so those are the formal ingredients. And now the actual construction. So, wow, maybe I can make it through all my talk at this rate. Are there any other questions to slow me down? Okay, so, all right, our algebra. So the algebra I'm going to describe in terms of its idempotence. So what I'm going to do is I'm going to draw two ends. So if when I'm slicing my diagram, I've got sort of n maxima, then I'm going to have 2n dots. When I do the slice, then I'm going to have 2n points. And my idempotents are going to be choices of regions. So those dots I'm going to think of as dots on the real line. And that divides the real line into these various intervals. And the idempotents in my algebra correspond to some collections of those intervals. And I'm going to denote those collections by putting big black dots. So in this case, I've got six places where my knot diagram crosses the horizontal cut. And I'm going to look at all the different ways of occupying 3 of those positions. Those are the idempotents in my algebra. The algebra elements, so the non-idempotent algebra elements, are paths that connect 2 of these idempotents. So I'm going to draw this. Here's one idempotent, here's another idempotent. I'm just going to look at sort of shortest paths that go from the top to the bottom. And we're going to introduce some relations. So what I should have said, and it's not on this slide, is that I have my algebra elements are these paths. And additionally, I'm going to have variables, U1, U2, U3, U4, U5, U6. So I'm going to have a polynomial algebra in as many variables as I had dots. Sorry, not dots, but positions where the knot crosses the real line. So in this case, I've got 6 possible variables. And one relation is that the one I didn't write down is that if I go from a position to its neighbor and I multiply it by the algebra element that goes from the neighbor back, that is equal to just the u variable attached to this position. So can you all see the blackboard okay? Oh, I can't see the screen when I'm at the blackboard. Can you see the blackboard okay? Is it okay?
Okay. Right big.
Okay, all right. So what I should have drawn there is that if I've got some idempotent that looks like this, and I've got another idempotent that looks like this, I go out from here to here, and then I go from here back to here. Then this product, and this is kind of the first position, this is the second position, this product is equal to just the first idempotent times U2. Out and back, I cross this strand twice, that's just multiplication by U2. All right, so 2 more relations. One is that if I've got a U variable and the corresponding strand is not, the idempotent doesn't occupy either the position to the left of it or the right, then multiplication by that, then that U variable is equal to 0. So that's a relation. So U variable is only non-zero if in the idempotents where that are occupied on either side of this wall. And the other relation is that my paths can't move too far. So if I'm moving 1 click to the left and then I move another click to the left, then when I try to stick those paths together, I'm trying to move twice to the left. I'm not allowed to do that. That's equal to 0. So these are the relations in the algebra. Is that clear enough? Octav, do you have something to ask or say? I don't hear you, but I
Yes, sorry, I was unmuted. So
okay.
What do you mean that, okay, if you go 2 clicks to the left, this you cannot do, so this is a relation. You mean that this operation is 0? Or
Yes, that's what I mean. That's what I mean.
All right, okay, good.
Yeah.
All right, thank you.
Excellent. Okay, all right, so that's the algebra, roughly speaking. So now I should tell you what the curvature is. So the curvature is specified by the matching on the upper diagram. So here's a picture. So if my upper diagram, say, looked like this, my real line I'm cutting, and it meets the knot in these 6 points, then I'm pairing up kind of the first position with the third position by a link component, then that's going to give me a term of u1 times u3 in the curvature. If I'm pairing here 2 and 6, that gives me a u2 times u6, and this could be a u4 times u5. Okay, so the if I've got n maxima, each maximum gives you a pairing between positions, and that gives you a term in the curvature. So in our case, this curvature will be u1, u3 plus u2, u6 plus u4, u5. Okay, is that clear? Well, there's a photo of Danny Ruberman on the beach. That's great. We spent a day on the beach last week and decided to come back. I thought it's a shame. I should have stayed at the beach, and then I could have made lots of people jealous, but I didn't do that. Anyways, generators have a marked minimum. So, I'm sorry. So, okay, so now I've described what the curvature is, and what I'd like to now say is what's associated to the very top. So the very top of the diagram, but if you just take your diagram, you slice off the very top of it, then you see some number of caps. And I need to define for you a curved type D structure over that curved algebra. So the curvature of the algebra, let me just remind you, is u1, u2 plus u3, u4 plus u5, u6. That should be a 6. Sorry. I've got one generator, and its differential is 0. And you might say, why is that compatible with what I've just said? Well, I want the differential. Okay, so what I should have really written here was that dx equals 0, and that's compatible because d squared equals 0. Why? Because d squared is equal to, so d squared equals 0, obviously, because d is 0. But why is that a curved module? Because the curvature equals 0. So it's formally a curved module. So that's the simplest curved module you can imagine. The curvature equals 0, the differential vanishes identically. So that's a very simple type D structure. And now for the content of this talk, which I haven't spoken about in public ever before, and that is the following. When you have this picture, then what we want to do is we want to, okay, so let me just talk about the more general pairing theorem. So I've told you roughly the algebra that goes into pairing a top with the bottom. But there's a generalization of that, which is what happens if you slice in multiple places. Is that clear? Is the picture okay? Yeah, okay. So now I've got my diagram. I'm going to associate bimodules to these slices. And what I want to do is I want to take a successive tensor product of those bimodules. So in order to be able to do the computation, what we need to understand is what are the bimodules associated to some very basic pieces of our diagram. So what are the basic pieces of your diagram? Well, you can have a bunch of strands coming in and they do a crossing somewhere. It can be this or the opposite crossing. A bunch of strands can come in. I guess you could have a cap. A bunch of strands could come in and you could have a cup. And the new thing that we need for links is that a bunch of strands can come in and you have a cup, but there's a big gray dot on the bottom of that cup. So that's the piece that you have if you have a link with many components. So what I now need to do is I'm going to describe what the bimodule is associated to a gray dot. And that's this picture. So the bimodule has, okay, so the generators of the bimodule correspond to, I'm going to put my gray dot on the leftmost strand. I broke down and using a blackboard top after all. So the generators are going to be all the different, as before, they're all the different ways of kind of occupying a position, occupying positions here. And in the leftmost part of the diagram, there are various ways that the generator can look. There are, I've drawn here 5 different possible ways and general generator types, which is to say, on the top of the diagram, I've drawn the incoming idempotent. On the bottom, it's the outgoing idempotent. So I can have a generator where positions 0 and 2 are occupied, and the outgoing idempotent is occupying position 0. Or I can have position 0 occupied and not position 2, and the outgoing idempotent is going to have nobody occupied to the left here. Or I could have 1 and 2 occupied incoming and then 0 occupied outgoing, or I could just have 1 occupied incoming and nothing occupied outgoing. This dot should be here. It should be in the 2nd position. Oh well. Okay, so these are the 5 different local pictures, and I'm going to just combine these 2 pictures into one, call it x0. These 2 positions I'm going to call x1, and this position picture I'm going to call x2. But please remember that this black dot should be over here. I apologize again. Okay, so I've got these kind of three shorthands for these 5 generators, and there are corresponding other generators called Y, which have the exact same structure. And now I'm going to draw a diagram, which represents all the actions on this picture. So I'm supposed to describe for you an A infinity module. And the A infinity module in this picture is going to have nothing bigger than an M3 action on it. So this is saying that if I take my generator called X1 and I M2 it with R2, then I get this generator X2. And if I M3 it with U2 L1, then I get Y0, and so on. So what you're supposed to check is that this creature that I've written down is actually a curved A infinity module with only nothing bigger than an M3 in it. I said bimodules. So what I've done here is I've only described what happens on the left, and you can extend these by the rest of the algebra in some way. Like for instance, I've got R2 here. Maybe I have R2 times R56. Maybe I've got some other algebra element that comes way out in the far out. Then the output is going to be X2 times, I would say R56, except it's really R54 the way I'm counting. So anyways, there's some way of extending this picture from a module that it looks, from the A infinity module that it looks like, to an A infinity bimodule in some sort of straightforward way. Okay, so that's that diagram. Okay, so this is what we associate to the local minimum. I didn't tell you what we associate to crossings or caps. I invite you to look in our paper if you're interested. This is actually, in some ways, the simplest module. Those are a little more complicated to describe. All right, but at any rate, I think I've given you now all of the algebraic input, except for the description of those modules, to compute link Floer homology. Are there any questions? Okay, so then
Peter,
yes.
Just as a sort of way to think maybe about this. So we in symplectic, sort of in the symplectic world, we are now used to this idea that you have this sort of passage through from modules over infinity algebras or bimodules, sometimes related to some cobordist type pictures in which you go from one end to the other. And the operation is a bit similar to what you say.
Yes.
Yeah, this is sort of what's going on in.
Yeah, I mean, yes, I think in some concrete way. Maybe I'll keep going out.
Interesting is a lot of the reflexes we have from either Legendrian contact homology or from immersed Lagrangian Floer homology is that certain pieces of what you say seem a bit familiar. So, for instance, the curvature looks a bit like augmentations, or in some other settings are called teardrops, counting of teardrops.
The curvature actually is counting holomorphic disk with boundary in one of the two Lagrangians. So
right.
Let me just keep going and
sure. Sorry, yeah.
So this is this sort of completely formal part of the talk, and probably the next part is there's going to be a little bit of topology, and then there's going to be the holomorphic curve counting that you like. So okay. So how do we prove the identification between these two invariants? The first step is that you start with your link projection, and you turn it into a Haggard diagram. So I don't want to explain what a Haggard diagram is, but here's an example. So I've got this link projection. So what I'm going to do is we're going to sort of imagine a surface that you get by, we're going to singularize the link projection and take a regular neighborhood of that. That gives you a little, and the boundary of that regular neighborhood now is a surface of some genus. And that surface is going to be equipped with a bunch of curves. So for each region in this diagram, I'm going to draw a red curve, which we call alpha curves. And at each crossing locally, we're going to draw a blue curve, which is a beta curve. Moreover, at the star, we draw a single blue beta curve that's like this. And at this gray dot, we're going to draw two things, which is a single blue curve like that and a single red curve like this. And we put on base points. At the starred regions, I have two base points, W and Z, on either side of that blue curve. And on this gray dot, I'm going to put a little red curve, and inside the red curve, I have W and Z. And where I put W and Z exactly matches with the orientation on the knot. Now, this is a symplectic manifold. We're going to take, this is a surface of genus G. We're going to look at its G-fold symmetric. This is a surface of genus, I guess, maybe G plus 1, however many alpha curves I have. We're going to take its symmetric product that's got a pair of Lagrangian submanifolds in it. And link Floer homology essentially is the Lagrangian Floer homology in the punctured surface where you puncture at these W and Z points. What I should say is that the intersection points between the two Haggard, these two tori, are in one-to-one correspondence with the Kaufman states that I described earlier. So we've known this diagram for a long time. We just didn't know how to count holomorphic curves in it. So the key point is going to be that we degenerate the diagram. We slice it, and that's how we slice the projection. And correspondingly, we can slice the Haggard surface to generate the Haggard surface. And when we do that, we get two kinds of diagrams. One is called an upper diagram, and a lower diagram. But here's a picture of a possible upper diagram. So here, in this upper diagram, I have what used to be these alpha circles. Now I've chopped them, so they become alpha arcs. And what I've got is I've got 8, in this picture, I've got 8 boundary components, right? So I had each of these cuts creates a boundary component on my surface. So I've got these various boundary components, and the beta circles remain circles. My alpha circles became alpha arcs. And what the holomorphic discounting that we're doing here is we're going to be counting in this case the third symmetric product of P1. So the third symmetric product of P1 comes equipped with this Lagrangian torus, which is the product of this circle, and this circle. That's a torus. And there's also sitting inside of it a funny singular Lagrangian submanifold, which is, I take this long arc over here and take its third symmetric product. So that's a pretty bad submanifold. But what I want to do is I want to look in a smooth part of that. So the bad part is when several of those points collide. And what I don't want to look in the region where, so my horizontal arc is subdivided into these 7 regions. And I never want 2 points to live in the same integral. So this horizontal arc, alpha 1, is divided into these 7 arcs, alpha 1 to alpha 7. And I want to look in the portion of the symmetric product where I'm not allowing 2 of those points to live on the same alpha arc. And that way I'm guaranteed to be in the smooth part of this Lagrangian manifold. And the 2 Lagrangians intersect a priori in the smooth part. So that's a good thing to do. So, so in some ways, the Lagrangian Floer homology I'm looking at is this Lagrangian Floer homology, this pair of, one is a smooth manifold and the other is a singular Lagrangian. And so now what's a differential? So here's an example of a differential. I've got a generator, which is a point in this 3rd symmetric product. I've got these 3 black dots. And what I'm going to do is I'm going to imagine that of those 3 black dots, I'm going to move 1 to the left. Everything else stays the same. Then there's a little bygone that goes from X to Y. And well, it's just bygone. And the way I'm going to record that bygone is to say that the differential of X is R2 times Y. So R2 is recording the fact that I'm moving to the left along this alpha arc. R stands for left. Okay. Another differential that you see is a differential from Y that goes back to X, which is another bygone, and it covers this this Z4 dot. So then what I'm going to do is I'm supposed to imagine the top of this is shaded, and what we have is that the differential of Y is L2U4 times X. So L2 comes from the top of this Z2, and the U4 comes from covering all of this Z4. Okay, is that sort of clear enough? So we're looking at holomorphic disks in this 3rd symmetric product of P1, and the algebra elements that are coming out are recording how my holomorphic disk interacts with these 8 distinguished points on this horizontal.
What is maybe less clear is why the differential doesn't mix up the different regions, and why, you know, I mean, for the definition of the differential, I think I mean, maybe there are other pieces that we don't see, but
oh, I didn't draw all the differentials. There are
right.
lots of differentials, and I've only drawn the differentials that look like they're in the 1st symmetric product. But in general, you're going to have kind of holomorphic disks.
But because of the 2nd Lagrangian is very bad, even if it has a generic part that's good. One worries that maybe this square will not respect any relations that's
yes,
reasonable, because in one parametric moduli spaces you will hit some bad parts, and then
okay, let me see what's on my next slide and imagine that maybe it has some. My next this doesn't entirely answer your concern, but it does talk about something. It exactly addresses an earlier remark you made, which is that d squared in this case shouldn't be 0. It should count holomorphic disks with boundary on the betas. And in this picture, you see that this blue circle goes around both Z2 and Z4. So you would expect that D squared should be equal to U2 times U4. There should be a term of U2 times U4 and D squared. And similarly, and actually the 2 disks that we saw, the one disk that goes from X to Y and the other disk that goes from Y back to X, the D squared of those is precisely equal to this U1 times U2 times U4 term. Okay. And I wanted to give a complete picture of a certain example. So if this is an upper link diagram, this is an upper link diagram. Here's its corresponding Haggard diagram. And this is now a computation simply in the first symmetric product. So you can actually just completely see all of the disks involved. You see that here's a, what I didn't draw was what the names of the generators are. There are 5 intersection points, X1, X2, T, Y1, and Y2. And you can see, for instance, there's this disk down here that goes from T to X2, and that goes underneath the Z2 thing, so that picks up this algebra element R2. So anyways, you can just take a look at this picture and you'll arrive at, you can enumerate all the disks and you'll see that you get this picture that we've drawn on the bottom. Now I think I'm going to start to talk about what you're worried about, which is that that of course the alpha Lagrangian is extremely singular. What happens if holomorphic disks try to enter the singular part of that? And the relations in our algebra are cooked up exactly so that we don't ever have to worry about holomorphic disks that wander out into that bad part. So d squared equals 0 would be killed if there were disks that went out into the bad part and then came back. But all such disks, they pick up an algebra element which we set equal to 0 in our algebra relations, and that's why they don't kill d squared equals 0. So here's an example. Suppose I've got this arc that goes across like here, and I've got these 2 beta curves that intersect like this. So I've got these 2 black generators and these 2 white generators. And what you can imagine is that I can go by a holomorphic disk that takes my x2 to y2 and leaves x1 fixed, and then a second holomorphic disk that goes from x1 to y1. So that's a term in d squared that stays precisely in the nice smooth part of my Lagrangian. And there's another way of canceling that, which is where I leave x2 fixed and I go from x1 to y1 first, and then I go from x2 to y2. That's another term in d squared, except it goes through the bad part of my Lagrangian. So really, we shouldn't be able to understand this so well in the first place. But the point is that in the algebra elements spat out in my algebra from this term in d squared formally equal to 0. So this kind of cancellation, we don't have to think about this kind of cancellation because it's hardwired algebraically. I don't know if that's a sufficient answer, but that's perhaps as good as one can give in a talk. Okay. Oh, I see. So, so maybe a word about how this is proved. The proof goes by. So a word about how we prove the pairing theorem. The pairing theorem is proved by you stretch the Riemann surface along those cuts and look at the fiber product description of the moduli spaces, and then by hand you put in some perturbations that make the this geometric description of moduli spaces algebraic. So that's the extremely quick sketch of that proof. But I think formally this goes until 10:15. And then there's a discussion period afterwards. Is that?
But you can take a bit more time, Peter.
Then I'll take a bit more time. Why not? This will be maybe the first time that I've actually spoken about all the slides in my projection. So everyone sit down. For another hour, I promise I'll be done. Okay. So what did I want to say? That the proof goes like this. So when we stretch normal to the we've got our Riemann surface. Well, the first thing I should say is that we use Lipschitz's cylindrical reformulation of Heegard-Floer homology, where one thinks of holomorphic disks in the G-fold symmetric product instead of as certain holomorphic curves in a disk times a Riemann surface. So that's sort of analytically easier to think about. And then the next point is that when you degenerate the Riemann surface, then holomorphic curves in the very degenerate surface are in one-to-one correspondence with holomorphic curves on the two sides that satisfy a matching condition. And the matching condition says that, well, the holomorphic curves go out to the boundary at the same time. And here time has one complex variable. There's a height. On the left and the right, what I've really drawn here are two disks. And what I'm saying is that the disks go out to the boundary along Rabe chords that are matched on the two sides. And they're matched in their ST components. And then there are some Rabe orbits that are also matched. So this is the first step in the proof that in the description of the differential. And the second step is what you would call moving orbits, which is to say that, okay, so analysis says that holomorphic curves in this big Heegard surface correspond to holomorphic curves that satisfy an exact matching condition. And then what we do is we perturb so if I call the horizontal component S and the vertical one T, then instead of having them matched exactly, I'm going to have S matched with R times S. So S on this side matches with R times S on that side. So that way, a Rabe orbit that happens on the right is matched with a Rabe orbit on the left that's a little further closer to the red boundary. And similarly, Rabe orbit over here on the left is matched with something. Anyway, sorry, I was saying the same thing again. So if I've got a Rabe orbit here on the right, that corresponds to a Rabe orbit on the left that's pushed a little further towards the red boundary. And what we do is and so you can define a differential in this context, and a continuation map argument will tell you that the two differentials give you chain homotopic chain complexes. And then you can take a limit as this parameter is pushed all the way out to the boundary. So as it's pushed out to the boundary, what you see is that orbits on the right are matched with curves on the left where the orbit degenerates to a long chord on the left. The other thing that can happen is that if you've got a pair of orbits, there are pairs of orbits that live on the same beta boundary curve. So if you've got two orbits, they can go as far out to the blue boundary as you want. And what they're going to match with is they're going to match with two orbits on the left-hand side where one of them is pushed out to the boundary and the other was somewhere in the middle. So that's a kind of limit that you get. The next step is you prune the curves, which is to say that we're going to, what happens when this orbit gets pushed out to the boundary, then there's some very standardly computable curves that you get at this east infinity, and you can just forget about them. So in the end, what you see is that if I've got an orbit on the right, that matches with a long Rabe chord on the left. And similarly, you can have a boundary degeneration on the left that matches with a pair, which consists of an orbit and a chord on the left. So, and the final step is maybe the most interesting, but it's an old story that we've done with Robert and Dylan, and that's time dilation, which is that I've told you now how to degenerate the S variable, and there's a corresponding degeneration of the T variable where, oh dear, view slideshow, sorry, where where these vertical gaps, you stretch the two vertical gaps with respect to each other, so that you see here an L7 and a U3. Well, what we're going to do is we're going to say that here's my L7 matching with this L7. The T difference, the vertical difference here is the same. But what I'm going to do is I'm going to start pushing that by a scale factor of tau. So the vertical distance here is tau times this vertical distance there. So in the limit, what we have is that the vertical distances are infinitely separated on the right side, and those correspond to finite separations on the left side. And this description is precisely the algebraic description that I gave earlier of the derived tensor product. So, so that's where the analytical picture eventually deforms and becomes exactly the algebraic picture that I defined earlier. And at that point, I've run out of slides, except in particular, I forgot to say the thank you slide that one typically puts at the end of a talk. So that's
all right. Thank you very much. So let's see if there are any questions.
This is Lisa. Jeffrey,
Hi.
You repeatedly talked about Riemann surfaces. Were you actually referring to something with a complex structure, or do you only mean a topological oriented object with dimension two-dimensional manifold?
I might have been vague. Of course, when you look at a Hegardt diagram, you just need a oriented two-manifold. But the minute we talk about Lagrangian Floer homology, we have to equip that two-manifold with a complex structure. So,
sure.
So if my Riemann surfaces weren't actually Riemann surfaces at the very beginning, they almost immediately became Riemann surfaces.
Okay, so when you use the word Riemann surface, that was what you meant. Thanks.
Yes. So you do have to check then, of course, that the answer is independent of the choice of complex structure.
Okay, thanks.
Hi, Lisa. I haven't seen you in a long time.
I haven't seen you either.
So, Peter, you mentioned this variant of Hegardt-Floer homology based on cylindrical version of.
Yes, yes.
So, can you say one more word about it? You said it very fast. So. Yes,
I did. I said it very fast. Okay. So the idea is the following: that white chalk. Where's my white chalk? Okay, here's my white chalk. Okay, so we're going to look at some symmetric product of a Riemann surface, and we have this pair of tori T alpha and T beta. And we're looking at holomorphic disks in that. So, these simply correspond to holomorphic curves in strip cross sigma,
right,
which intersect the generic fiber in D points. And the correspondence is pretty clear. You just, those D points is a point in the default symmetric product. But so Lipschitz kind of laid out the foundations of the Floer homology that you get by just thinking about it from this point of view. So we can forget about the default symmetric product and just think about holomorphic curves in this space. And now directly to get transversality and so on, you need to move in the space of almost complex structures you're choosing on sigma, and so on. But the basic correspondence comes from sort of this algebraic geometry perspective, and Lipschitz's theory allows one to just then forget about this big dimensional complex or symplectic manifold and think just about curves in sigma cross disk, which degenerates a little. It's a little easier to think about how it degenerates when you do the pinching.
And this becomes more combinatorial, or it's easier combinatorially understandable, or?
I would say it's easier to understand analytically in the sense that when I degenerate, so the degeneration that we're doing to the Riemann surface is that we're taking it's developing some nodes. And there are people who understand how the symmetric product degenerates when you introduce nodes. So if you introduce nodes into your surface, you look at how the complex structure on the G-fold symmetric product degenerates. There are algebraic geometers who study that, and one could try to work in that story, but it's actually easier to think about if a Riemann surface degenerates nodes, you see exactly what's happening, and you can then see what's happening in the holomorphic curves. So I would say that it's not so much that well, ultimately you can see what's happening combinatorially, but that's not the I'd say the key advantage is this kind of the analysis is simpler.
Maybe there are other questions. I see that. Let me see on the chat if there's any.
Can I ask a question?
Yeah.
So go back to the Hager diagram, and you have Hager diagrammatically, you have this doubling of generators for the ladybug effect.
Yes.
But you just build it in algebraically, I guess, and you still just go Kaufman states, and
oh no,
that's what makes. I spaced out maybe for a few minutes.
No, that was a sleight of hand. That was me being mildly dishonest. In fact, there's a doubling of generators, and when you look at the actual multivariable Alexander polynomial, then I divide it out by that doubling of generators. But indeed, you're right that in the actual Hagar diagram, you get 2 to the L-1 as many generators as you do Kaufman states. And in fact, there's a little further story, which is that that you need to do some admissibility so that you get even right. So the diagram, the Hagar diagram itself is maybe a little uglier than what when you actually do the computations, you have to do some moves.
And you put them special places, like where you have the constraint.
The Hagar diagram of a single gray dot. We want to compute its module. Then we do that by doing a little finger move that increases the number of generators. But the answer is independent of that choice. So that's the bit that was swept under the rug there.
So Peter, you can turn off your screen share, because for this discussion, I think people
yes,
see you bigger, and if you write on
we can maybe see your blackboard.
Yeah.
Yep. Okay, great.
Which we couldn't easily. That's better, much better.
No, it's just my head that's in the way of the blackboard.
Yeah, well, it won't be if you write on it.
So, so I had I don't know, maybe there are other questions. I have another one myself, but might be some other questions around here. So I don't see anything. Right, so my other question is that to me it looks very intriguing that you kind of resolve this issue of sliding in this bad part, say, of the Lagrangians through algebra, because in general we are not quite able to do that. When we write, it means that you understand extremely well how things can degenerate in this part, because otherwise you wouldn't be able to write these relations, I guess.
I think you're giving me too much credit, but I'm trying to say, what I want to say is that those degenerations don't affect squared equals 0 because the algebra element that they would contribute is 0.
Mm-hmm.
So somehow I did the opposite of what you're giving me credit for doing, which is that instead of understanding how things degenerate when they enter the bad part, I'm arguing that the canceling good terms in d squared equals 0 are irrelevant because the outgoing algebra element is 0. So
right. Oh,
I guess the miracle is that it works.
yeah.
The miracle is that at the end of the day, you get a reasonable pairing theorem where you didn't have to worry about these.
Yeah, because you see, in most of the things that we do with Lagrangians is we try to have them as regular as possible. Even when they are immersed, we start to have a bit of problems with, but suppose immersed is perfect, but if they would have some singular parts, that would be a significant issue for, I don't know.
So maybe this is something,
stuff like that.
So maybe here's another point, which is that the singular Lagrangians are really singular Lagrangians from the point of the view of the symmetric product.
Mm-hmm.
When you look at it from the point of view of Lipshitz's theory,
Mm-hmm.
The badness is much less bad. Somehow the badness, there's what's called boundary monotonicity, which is that you want, or a strong boundary monotonicity is that, which is that you want one point on each alpha arc. You never want more than one point on each alpha arc.
Mm-hmm.
And it's that condition that you have to see that you can work entirely inside of that world. So maybe that's easier to understand than to say that I have a Lagrangian that has singular points and we're not.
Yeah, no, it's much. Yeah, that resonates with you know. Okay, so thank you very much. Let's see. Maybe there are other questions. So today people haven't used chat too much, but okay, it's
because I haven't even turned it on. So
I have a question.
Okay.
The dependence of the link Floer homology on L, it's related to the comment you had to the previous question. Is this really the dependence on the number of components of the link, which would be a topological thing, or the choice of which symmetric product you're using? In other words,
no. This story sees a lot of L. It doesn't just see kind of. If you're asking how is L seen in this picture, L tells you how you're choosing your Lagrangians actually. And the theory actually sees a great deal of L. It sees its multivariable Alexander polynomial and it sees its Thurston polytope. So it's not, it sees a lot of L, I guess is my point.
My question is, when you say you're computing Alexander polynomial of a link,
yes.
You're computing the Euler character is computing that. It's computing that up to this multiplicative factor, right?
Yes. Well, okay.
So my question is, that multiplicative factor, does it mean that really you're not honestly computing a link invariant? Because I can always draw a wrong diagram, which is a stupid one where I would represent and say an unknot in a symmetric product of, I don't know.
I understand. No. There is no. There's a way to nail down the combinatorial factor in link Floer homology. So, if you're looking at a knot, then there's a way of nailing down the multiplicative factor, which is to say that the Alexander polynomial should be a symmetric function in T. The reason that doesn't work for links is that the Alexander polynomial might be identically 0. But it turns out that knot Floer homology has a certain symmetry in it. And that symmetry nails down the multiplicative, what we're used to as the multiplicative factor. So that can also be nailed down in a way that is, yeah.
In any one computation, I suppose, it's not an issue, but does your theory give link invariance in the sort of honest old sense of the world, where nothing depends on any kind of presentation you choose?
Yes, yes. I should have probably started by saying that. The way I drew my link, it had a lot of choices, but in fact, the invariant at the end of the day is just an invariant of the link.
Thank you.
Peter, in the chat, I requested a page reference for the page of your not homology book that you held out.
Okay. Oh, by the way, it's also available. It's on my home.
Available from a. Oh, okay.
So if you don't want to, you should. Everyone should go out and buy the book. But
yeah. Okay. Well, however we get. Okay. No, but what's the page reference?
It is page 2.
Oh. Really? Okay. Thanks.
Yeah, page 2.
Thanks.
So we just have to buy the first 2 pages, Peter.
Yeah, no, you don't have to buy it even. You can download it for free on my homepage. But then you
Okay.
see it and see that you have to buy the book.
Okay.
Absolutely. We will. Everyone will go and buy it. Great. So
Thanks a lot.
let's see, maybe some other questions. So, yes.
Hey.
Hi. Can you do like the scan exact sequence and such in now using now that you have this all down for links? Can you prove that with some local computation?
It should be doable with a local computation. I haven't done it.
You should give it to Mike Wong. No, I was going to say give it to Mike Wong.
Yeah, no.
After his collection.
There's also some very nice work of Nate Dowland, which probably also I don't know if he proves it or certainly. I think it's very close to a proof if it's not a proof. I don't remember what he claimed, but yeah, there are many things that one could try to do from this perspective. This perspective is good at some things and not so good at others. For example, coming back to Mina's question, it's not so easy to prove that it's a link invariant from this algebraic perspective, because there are these various choices of a distinguished link component and where you put the little gray dots. So we don't give an independent proof that this is an invariant. We just prove that it's isomorphic to an earlier constructed invariant. So that's an example where this is not ideal, but it's good in that it's much more tractable for computations. Any other questions?
Yes. What about a cornered concordance invariant now that we have all these tango things going on? I don't know.
That sounds like an excellent idea, Ina. Go for it. Yeah, I don't know. Yeah, of course, that sounds like a very worthwhile project. Anything else?
So Peter.
Yes.
I heard that this stuff is much faster than anything used before to compute non-Floer homology.
Yes.
Why is that? I mean, it seems pretty horrible, the algebra, to me. What makes it fast?
The thing that the great advantage is that you have much fewer generators. The thing that kills grid diagrams is memory. So you have to keep track of too many generators. Whereas this one has almost an, I mean, I don't know how to formulate that mathematically, but essentially an optimal number of generators. it's true that the differential has to work hard, but the answer is that it just has so much fewer generators.
So what's the current state of the art in like being able to compute, you know?
What?
How many crossings are you guys now up to, like able to compute easily?
I'm sorry, you're gonna have to ask Zoltan for that. I haven't run it very. Zoltan actually has some code on his homepage that you can use, and I don't think it's yet for links, but he assures me that that's easy to implement as well.
So the not version you guys do over Z, is this, you could do that too? Can you show it's the same as the original HFK over Z?
We didn't prove that it's the original HFK over Z. We did construct it as an invariant over Z, but we didn't prove that. We didn't identify. I don't imagine that would be too difficult, but one would have to keep one's conventions straight and so on.
Okay, well, fantastic. So let's thank Peter again. So Peter, thanks again for
Thank you.